Our application consists of 3 stages. Stage 0 is the language selection. Stage 1 is the web crawling. Stage 2 is the language checker. In stage 0, the user selects one of the 3 language options. In stage 1, the crawler crawls through the web to collect textual data in the selected language and stores the data in a text file. In stage 2, the checker looks for misspellings and grammar errors and outputs a list of suspicious phrases and suggested spelling corrections. The crawler makes an API request for random Wikipedia topics. For each of the topics in the returned list, we gather textual data from the page and then recurse on up to 30 links embedded in that page. For each page visited, the crawled data is stored in the appropriate text file for that language. First, we build the language model from the crawled data. The crawled data file is read and parsed into lines, and each line is split into unigrams and bigrams. Each bigram is also tagged using OpenNLP tools to obtain the POS. The unigrams and bigrams and POS pairs are all stored in their respective hash tables. In the end, our language model consists of hash tables that store the frequency of the unigrams, bigrams, and POS pairs seen in the data. Next, we build the noise model. We iterate over a database of the most common misspellings in the English language and calculate the Levenshtein distance between each misspelling and the corrected word. We use the Levenshtein distance to determine the minimum transformations, such as deletions, insertions, and substitutions, necessary to correct the misspelled word. Each transformation is added to the hash table. In the end, our noise model consists of a hash table that stores the frequency of each transformation. The input text is split into lines, and each line is split into words. We look up each word in the language model. If the word is found, it is deemed not suspicious. If it is not found, then it needs to be further evaluated. First, we generate all words that are edit distance 2 away from the word in question. Of the newly generated words, we discard any that are not part of the language model. Of the remaining words, we look up their frequency in the language model and pick the word that has the highest frequency. If that word is the same as the original word, then we classify it as not suspicious. Otherwise, we consider it suspicious and output a correction and a confidence level. This new word is chosen as the correction for the misspelled word. The suspicion level is set by dividing the word's frequency by the total frequency of all words in the language model. The input text is split into lines, and each line is split into bigrams. We look up each bigram in the bigram hash table of the language model. If the bigram is found, it is deemed not suspicious. If it is not found, then it needs to be further evaluated using POS analysis. The bigram is tagged to get the POS, and then we look up the resulting POS pair in the POS hash table of the language model. If the POS pair is not found, we flag it as highly suspicious. If it is found in the hash table, we calculate a confidence score based on its frequency in the language model. To calculate the suspicion level for an unseen bigram, first we look up the frequency of the POS pair in the hash table of the language model. We utilize the distribution of the POS pairs in the language model to calculate the mean frequency and standard deviation. And then we use those estimates to create a cutoff value. The cutoff value is the mean plus half a standard deviation. Note that this calculation needs to be performed only once when initializing the checker. If the frequency of the POS pair for the unseen bigram is greater than the cutoff, then the bigram is not suspicious. If the frequency of the POS pair for the unseen bigram is below the cutoff, then we assign a confidence score that is scaled frequency from 0 to 100, where 0 is less suspicious and 100 is most suspicious.